everyone, thank you so much for clicking onto the video. Today's learning objectives are all to do with electron configuration. So we're going to look at electron configurations of atoms and ions up to Z equals 36 in terms of shells and subshells, so the orbitals sp and d, and we're also going to look at ionization energies. So by the end, we should be able to define first ionization energy, write equations for first and successive ionization energies, and explain how first and successive ionization energies in period 3 and in group 2 give evidence for electron configuration in subshells and in shells. So now we're going to talk about electron arrangement. And electrons are arranged in energy levels or electron shells, which we've seen before at GCSE. And these energy levels actually have subshells. And we have the existence of S, P, D, and F subshells. And each one of these subshells then consists of electron orbitals. And orbitals are just regions of space where electrons are likely to be found. Each of these orbitals has a number, and this tells us the main energy level, so the electron shell that it corresponds to. So for example, if it's in the first energy level, or the first electron shell, then it'll have a number 1, and then we'll have 2 for the second main energy level, and so on. And so we can use an energy level diagram to represent atoms and their electron shells. So here we have an energy level diagram. So on the y-axis, we've got energy, and on the x-axis, we've got the distance from the nucleus. So for example, looking at 1s. 1s is the first shell because it's got number 1. And so that's why it's the closest to the nucleus. Because if you think back to GCSE, we have the nucleus, and then we have the first shell of electrons around the nucleus. And so it's the closest to the nucleus. And we also find that if we go further and further out, so when we get to higher and higher main energy levels, the energy increases. So for example, the fourth shell will have a much higher energy than the first shell. And so quickly running through subshells and the orbitals. For the first main energy level, we only have one subshell, and that's the S subshell. And the S subshell consists of one orbital, which is the S orbital. And then the second shell, we have two subshells. So we have the S subshell and the P subshell. And the S subshell comes as one orbital, and the P subshell comes as 3 orbitals. And then for the third shell, we have the S and the P again, which is exactly the same. And then we also have an added D subshell, and this is split up into 5 different orbitals. And then for the fourth shell, we then have an added F subshell, which then has 7 orbitals. So quickly summarizing that, what the number represents is the main energy level. Which is basically the electron shell. And then we have the letters S, P, D, and F, and these are subshells. And then if we look at an individual box like this one, what we call this box is an orbital. And so now we're going to look at how to fill out these energy level diagrams. So firstly, we need to look at a few rules, and this will help us fill the diagram out. So the first rule is that electrons are filled into the lowest available energy level first. And then electrons prefer to occupy orbitals on their own. And one really, really important rule is that 4s fills and empties before 3d. And this makes sense because we know that electrons are filled into the lowest available energy level first. And if we look back at the energy level diagram, the 4s orbital is actually of a lower energy than the 3d subshell. And so that's why 4s gets filled out before the 3d subshell. And then finally, any single atomic orbital can hold a maximum of 2 electrons, and they have to have opposite spins. And what we mean by opposite spins is that one will spin clockwise, whilst the other one will spin anti-clockwise. So, for example, if we look at how to fill out the energy level diagram for silicon, the first thing we do is look at the periodic table and see how many electrons silicon has. And it actually has 14 electrons, and so that's how many we need to fill out. So using the first rule, we need to fill the electrons into the lowest available energy level first. So the lowest available energy level in this case is the first shell, because we don't have any electrons yet. And so we can fill out 2 for this 1s orbital. Because you might think, because electrons prefer to occupy orbitals on their own, that this second electron would go into 2s. But this rule is actually overridden by the first one, because electrons are always filled out into the lowest available energy level first. And so we've now filled out 2 electrons, and so now we fill out 2s. So we have another 2 electrons, and I draw them like this because this indicates the spin. So we have one which is spinning, let's say, clockwise, and the other one which is spinning anti-clockwise. And then we fill out 2p. So now we need to remember our rule about how electrons prefer to occupy orbitals on their own. So we fill out 3 separately first. So we have 1, 2, and 3. And then we can fill out the next 3. So we have 1, 2, and 3. So now we fill out 10, so we need 4 more. So we fill out 3s with 2 electrons. And now we need another 2 electrons. And so now we need to remember about how electrons prefer to occupy orbitals on their own again. So we need 1 in this orbital and a second one in this orbital. So this is our finished energy level diagram for silicon. However, if we were going to look at something like calcium, so calcium has 20 electrons. So we're looking at calcium, and it has 20 electrons. So right now we've filled out 14, so we need 6 more. So if I continue this energy level diagram, we should be able to get the energy level diagram for calcium. So add another 1, and then we add another 3, like we did for the 2p subshell. So now we have an added 4, and now we need 2 more. But now we need to remember our rule about how 4s will fill before 3d. And so we need to fill out 2 electrons into 4s instead of any in the 3d. And so this would be our energy level diagram for calcium. And we can also write out the electron configurations of atoms without using a diagram, so a shorthand method. And so, for example, we're going to look at how to write out the electron configuration of calcium. So calcium we've just seen, and we've just drawn on the energy level diagram. And so we can just take that and convert it into a shorthand way of writing it. So we have 2 electrons in the 1s orbital. And so what we do is we have 1s, and then we put in a 2, which just indicates that we have 2 electrons in that orbital. And then we have 2s, and we also have 2 electrons, and so we put number 2 there. And then we have our 2p subshell, and instead of writing out all the orbitals, we just write out the subshell. So it has 6 electrons in the total subshell, so we have a 6 on top of the 2p. And then we have 3s, which has another 2 electrons. And then we have 3p, which has 6 electrons. And then we have 4s, which has 2 electrons. So like the energy level diagram, we miss out the 3d. So this is our electron configuration for calcium. And now we're actually going to look at what this kind of means on a periodic table, so what the relationship is. So going to the periodic table, we can actually split this up into blocks. So if we look at this block here on the left, and if I split it off like this and draw it into a rectangle, this block is what we call the S block. And what that means is just that the outer electrons are in an s orbital. And then we have the block in the middle, which is all the transition metals. And this block is what we call the D block. So all of their outer electrons are in a D orbital. And then finally, on the right-hand side, we have the P block. So if I split it up like this, this is what we call the P block. So all of their outer electrons are in a p orbital. And actually, hydrogen and helium are both in the s block as well. And how we get this number in front, so the energy level, or the electron shell. So for example, here we have 2. How we get this 2 is this is actually the period number. So it's the number of the row. So for example, we have lithium here, and this is an s block, so we know that the outer electron is in an s orbital, and it's also in period 2. So that means that the outer electron must be in a 2s orbital. And so the electron configuration for lithium is actually 1s2 and then 2s1. So for hydrogen, we have 1s, because we fill out the 1s orbital first, and we have 1 electron. And then for helium, we would have 1s2, because we can fit 2 in this 1s orbital. And then we start to fill out the 2s orbital, and that's why lithium is 1s2, 2s1. So for example, if we wanted to work out, let's say krypton here, instead of counting all the way across the periodic table, we can simply work this out by just looking at the block and the period it's in. So it's in the p block, so that means that the outer electron is in a p orbital, and it's also in period 4, and so the outer electron must be in a 4p orbital. So the electron configuration for krypton is 1s2, 2s2, 2p6, 3s2, and then we have 3p6, and we have 4s2, so we need to remember that that comes first before the 3d, and then we have 3d10, and then we have 4p6. And how we know it's 4p6 is because the p block for period 4 starts with this gallium. And so counting along, we have 6 until we get to krypton. Because gallium would be 4p1 because it's the start of the p block. And then germanium would be 4p2, arsenic would be 4p3, and so on. And so that's why krypton would be 4p6. And there's actually 2 really, really important exceptions that we need to look at. And those are chromium and copper. So firstly, if we look at chromium, which is here on the periodic table, it's in the D block, and it has 4 electrons in a 3d orbital. So what we would expect it to be would be 1s2, 2s2, and then 2p6, 3s2, 3p6. So this would take us to argon, and then we'd have 4s2, and we'd expect it to be 3d4. However, this isn't the case because chromium likes to only have 1 electron in the 4s, and this happens because of the closeness of the 4s and 3d subshells. So instead of having this, so this is wrong, we have 1s2, 2s2, 2p6, 3s2, 3p6, and then we have 4s1. So only 1 electron is put into the 4s orbital. And so that means that we would have to have 3d5 to account for that extra electron. And then looking at copper, we have a similar thing. So copper is here, and so we would expect 9 electrons in this 3d orbital. So we have copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. However, this is wrong again because copper is also an exception and it likes to have one electron in its 4s orbital instead. And so what we have is 1s2, 2s2, 2p6, 3s2, 3p6, 4s, and then 1, and then 3d10. Because again, we have an extra electron that we'll need to put in the 3d orbital. And also something really important to notice is that even though I said that you could work out using the period which main energy level the electrons are in, well, the outermost electrons are in, it's not entirely true, because if we look at the D block, the first period of the D block is actually in group 4, but those electrons, those outer electrons are in the 3d orbital, like we have for chromium and copper. And so for the D block, we always have to -1 from the period to find which main energy level the outer electron is in. So we're now going to have a look at ionization energies of group 2 elements. So first ionization energies usually decrease down a group. And this is because of two reasons. So firstly, let's go through the definition of first ionization energy. So again, the first ionization energy is the energy required to remove the outermost electron from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. And we have three factors which could affect ionization energy, and those are the nuclear charge, the distance from the nucleus and outermost electron, and also shielding. And so we have two reasons why first ionization energies will decrease down a group. And so the first is that the distance from the nucleus increases. And this is because as we go down a group, we add an electron shell each time because they're in different periods. And so that's why the distance from the nucleus increases between the outermost electron and the nucleus. And this actually also causes shielding to also increase, because shielding just means how many electron shells basically you have between the outermost electron and the nucleus. So overall what we have is that the outermost electron feels a weaker attractive force towards the positive nucleus as we go down group 2 or down any group. And so because of this, it takes less energy to remove this electron, and so its first ionization energy will decrease as we go down the group. So for example, let's look at magnesium. So magnesium is in group 2, period 3, and it's in the S block. And so its outermost electron must be a 3s2. So we have 1s2, 2s2, 2p6, and then 3s2. So this is our magnesium. However, when we look at calcium, which is down 1 in the group, it's also in the S block because it's in the same group. And because it's in group 2, it also has 2 outer electrons in its outer orbital. But this time it's in period 4. And so the outermost electron is now in 4s2. So we have 1s2, and then 2s2, and 2p6, 3s2, 3p6, and then 4s2. And if I draw this on an energy level diagram, it'll become a bit clearer as to why calcium's electron is easier to remove. So for an energy level diagram, we have the energy going up on the y-axis, and on the x-axis we have the distance from the nucleus. So we have our 1s2, and then we have 2s2, 2p6, so those are 3 orbitals, and then we have 3s2, and then 3p6, and then we have our 4s2. Normally we would have our 3d10, but remember that 4s is of a weaker energy compared to 3d. So therefore we have a 4s first. So we can label these. So this would be 1s, 2s, 2p, 3s, 3p, and then 4s. So first filling out for magnesium, and we have everything up to 3s2. So we have 2 in here and 2 in here, and then we have all of these filled out, but remember that they like to fill out individually first. And then we have 2 in this 3s box. So this is magnesium. However, if we wanted to add in all the electrons for calcium, we would have to add in these extra electrons. So we'd have 6 in the 3p subshell, and then another 2 in this 4s orbital. And you can see if I put a line here, then these two are at a higher energy level. Than the orbitals 1s, 2, 3s. And so these electrons are much easier to remove compared to everything which is below this pink line. And so if we wanted to remove one of these electrons, which is what we're trying to do to obtain the first ionization energy, then it's very, very easy to remove because there's more shielding from the attractive nucleus, and also the distance between this electron and the nucleus has increased. And so it feels less of a force towards the positive nucleus, and so it's easier for us to remove and it takes less energy. And so we have a lower ionization energy required to remove it. Now we're going to look at the first ionization energies of period 3 elements. So the definition of first ionization energy is the energy required to remove an electron from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. And so we have the general trend that the first ionization energies increase along a period. And this is because of 2 reasons. The first is that nuclear charge increases. So there's a stronger attraction between the positive nucleus and the outermost electron. And the second is that the amount of shells, the number of shells in each period 3 element is the same. It's just 3 shells. And so they all have similar shielding, a difference. And so overall, the attraction to the nucleus that the outermost electrons feel increases along the period. And it takes more energy to remove it as you go along the period. And hence why the first ionization energy generally increases along the group. However, there are 2 important exceptions. So first we have aluminium. And this is because the p electron is in a higher energy level than the s electron, so it takes less energy to remove it. So if we have a look at the electron configuration of aluminium, we have 1s2, 2s2, 2p6, 3s2, and 3p1. And then the electron configuration for magnesium is 1s2, 2s2, 2p6, and 3s2. And so we see that this electron and the 3p1 is in a higher energy level compared to the electrons in the 3s's. And so it takes a lot less energy to remove that electron. And so the first ionization energy of aluminium will be lower than for magnesium. The second exception is sulfur. And this is because 2 of its p electrons are paired in a p orbital. So one of these will be easier to remove than an unpaired one due to the repulsion of the other electron in the same orbital. So if we have a look at the electron configurations of phosphorus and sulfur. So phosphorus we have 1s2, 2s2, 2p6, 3s2, and 3p3. And then for sulfur we have 1s2, 2s2, 2p6, 3s2, 3p4. Now initially we don't really know, we can't really see why sulfur will have a smaller ionization energy. But if we draw out the different energy levels on a diagram, it becomes a lot easier to see. So if we have the 1s and then 2s, then we have 2p and 3s and then 3p. So I'm drawing this in increasing energy. And so if I fill out for phosphorus, so we've got the 1s2, and then we have 2s2, and then we have 2p6, but remember that they always have to fill out one by one first. So we have 3, and then we have the other 3, and then we have 3s2, and then for phosphorus we have 3p3. So we have 3 electrons, and they're all separate. However, for sulfur, we have an extra electron, so we have 1 electron here. And so this means that one of these electrons in this suborbital will be easier to lose. And that's because of the repulsion between these two electrons. And so that's why the ionization energy for sulfur is smaller than for phosphorus, because in phosphorus, the 3 electrons are all in separate suborbitals, so they don't feel any repulsion. So it's less easy to remove that outer electron. And this trend that we see in period 3 elements is actually the same for period 2. So it can be applied to other periods. And this is because in the periodic table, the trends carry along, so the trends repeat every period. So now we're going to talk about successive ionization energies. So these are basically, we're taking an electron away, and then we keep on taking electrons away. And so we get successive ionization energies. So looking at this graph, what we have is the log of the ionization energy on the y-axis, and then the number of electrons removed on the x-axis. So we can see for this sodium atom that the first electron removed, which is this one here, takes the lowest amount of energy to remove. And then we have a big jump, and then we have a set of 8 electrons, which also increase in the ionization energy needed to remove them. And then we have another big jump again, and then 2 more electrons. And so we're going to go into more detail about why we have this. So this actually gives us some evidence towards electron shells, because if we think about sodium, what we have is, if we write out the electron configuration, sodium is in group 1 and it's in period 3, and it's also in the s block, and so its outermost electron will be the 3s1 electron. So we have 1s2, 2s2, 2p6, and then 3s1. And as you can see, the number of electrons in this electron configuration add up to the number of electrons on this graph. So if we think about it, and so first we're removing this 3s1 electron, so we're removing this electron. This is in a higher energy level compared to the 1s and the 2s and the 2p, because it's in the third shell. And so there must be more shielding between this electron and the nucleus, and also the distance between this electron and the nucleus will be increased compared to the first shell and the second shell, or electrons in the first and second shell. So this electron will take the least energy to remove because it's in a higher energy level. And so this is the electron we see here. So this must be our 3s1 electron. And then we have this massive jump here, where the ionization energy increases by a significant amount. And this is because we're moving electron shells. So we've got rid of an electron shell. So this is the jump between electron shells. Because after we remove the first electron, the second electron which we're going to remove is in a 2p, and the second shell is of a lower energy level compared to the third shell. And so that's why we get this massive jump. And then, as you know, we have 6 electrons in the 2p subshell. And so we have 6 electrons which are increasing. So we have 1, 2, 3, 4, 5, and 6, which are all increasing in ionization energy. And the reason why the ionization energy increases during this 2p subshell is because if you think about it, if we have, so after we remove the second electron, so this electron here, we have a sodium 2 plus electron. But then if we want to remove another electron, we then produce an Na3 plus ion. And so that means that every time we remove an electron, we're removing the electron from a more positive nucleus. So first of all, we're removing an electron from this Na2 plus. But then after we've done that, we then need to remove the next electron from an Na3 plus, which will be stronger than the 2 plus. And so that outer electron will feel a bigger force towards the positive nucleus. And so that's why the ionization energies increase during an electron shell, or the subshell, which is 2p. And so after we've had these 6 electrons removed, we then remove another 2. And so these 2 are our 2s ones. So these are our 2s electrons, and the ionization energy also increases. And there's not a very big gap between the 2p and the 2s, because if you think back to the energy level diagram, there's not much energy difference between the 2p and the 2s. So the 2p isn't very much higher in energy compared to the 2s, because they're both still part of the second energy level. So these ones here are the 2p electrons. And then we have this massive jump again. And so again, this signifies that jumped an electron shell. So we've decreased by another electron shell. So we have a jump to the next electron shell. And then we have 2 electrons. So these are our 1s electrons. And so they take the most energy to remove, because we have a very, very positive ion now. So we have an Na9 plus ion now. So it's very, very positive. And also there's literally no shielding anymore, because we're at the first electron shell. And so the distance between the outer electron and the nucleus won't be very big. And so it'll take a lot of energy to remove these 2 electrons. And so that's why they have the highest ionization energies. So using some of these graphs, we can actually determine the electron configurations of atoms, because depending on where the big jumps are, we know when we go down an electron shell. And so we can see from this graph here that because there's 1 electron right at the bottom before a big jump, this atom, if we didn't know this, this atom must have 1 electron in its outer shell, and then it has 8 in its second shell, and then finally 2 in its first shell. And so we would be able to deduce that this atom is a sodium atom. So now we're going to look at ionization energy equations, and we're going to quickly run through all of our definitions for ionization energies, and these should help us with writing out the equations. So first of all, we know that the first ionization energy is the energy required to remove 1 electron from each atom in 1 mole of gaseous atoms. And this is going to form 1 mole of gaseous 1 plus ions. And so really key things to remember here are that we're only removing 1 electron, and it's from each atom, and it's in 1 mole, and everything is in their gas phase. And then for the second ionization energy, that's the energy required to remove 1 electron again from each ion in 1 mole of gaseous 1 plus ions. And this is going to form 1 mole of gaseous 2 plus ions. And so you might think that the second ionization energy is the energy required to remove 2 electrons from an atom, but that's wrong, because it's actually the energy required to remove 1 electron from a 1 plus ion to form a 2 plus ion. And so we have that it's the energy required to remove 1 electron from each ion in 1 mole of gaseous 1 plus ions to form 1 mole of gaseous 2 plus ions. And so we can form a general definition for the nth ionization energy, where n is just a number. And so this ionization energy is the energy required to remove 1 electron from each ion in 1 mole of gaseous, and we've got n minus 1 plus ions, to form 1 mole of gaseous n plus ions. So for example, if we had the fifth ionization energy. That'll be the energy required to remove 1 electron from each ion in 1 mole of gaseous 4+ ions to form 1 mole of gaseous 5+ ions. So we're going to look at writing out the equation for the first ionization energy of sodium. So we start off with a sodium. And now we need to remember our definition and how everything is in their gas phase. And so we have to put in a state symbol, which will be a G for gas. And then what we do is we remove an electron. And so it's convention to write electrons as a gain instead of a loss. And so that's why we put that reaction arrow here. And then we have 1 mole of Na+ ions, which are also gaseous, and we have an electron. Instead of having Na minus an electron, goes to form Na+. So it's just convention to write it this way. And then if we're looking at the second ionization energy of sodium, remember that we're removing 1 electron from 1 mole of gaseous 1+ ions to form 1 mole of gaseous 2+ ions. So we start off with this Na+, which is a gas, and so we do exactly the same thing. So we have the reaction arrow, and then we have Na2+, and we have an electron because we've lost another electron, and so the positive charge increases by 1. And so for the equation for the fifth ionization energy of vanadium, what we have is that we need to remember that we've got N-1+ ions to start off with, and then we're forming 1 mole of gaseous N+ ions. So the N-1 would be 4, so we would have vanadium, which is V, and so we'd have V4+, and that would be a gas, and then we would have the reaction arrow, and then we would have V5+, which is a gas, and then we would have an electron. So now we're going to move on to some questions. So for question 1, the following table gives the successive ionization energies of an element in period 3. For A, identify the element. So what we need to remember here is that successive ionization energies give evidence for electron shells. So all we need to do is identify where the biggest gap is in ionization energies. So firstly, what I like to do is just look at the first one. So here we have a gap of around 800. And then here we have something bigger, and this is about 1,500, let's say, or 1,700. And here we have about 1,100. And then from the 4th to the 5th, we have about 12,000. And then this last one, we have about 3,000. So they're just very, very rough estimates of the differences in ionization energies we have. But we can see that this one here is our biggest jump in ionization energy. And so for A, this tells us that this element is in group 4. And that's because if we think about it, first when we remove the first ionization energy, it takes 786 kilojoules per mole. And then the second is a bit more, the third is slightly more, and then the fourth is slightly more. And so that means we must have 4 electrons in this outer shell, because after this fourth one, the ionization energy for the 5th electron is a lot higher, and that means that we've jumped an electron shell. And so we've got 4 in the outer shell, and then we have 2 in the inner shell. So what it looks like is we have the nucleus, and then we have 2. So this is electrons 5 and 6. And then this outer shell, we have 1, 2, 3, and 4. And so the first 4 electrons don't take nearly as much energy as the 2 in the middle. And so this indicates to us that we have something in group 4. So this is a group 4 element. And because we know it's in period 3, this means that this element is silicon. And then for B, explain why the ionization energy of every element is endothermic. Endothermic means that we're putting energy in. And the reason why is because energy is required to remove electrons from atoms. And that's what we're doing when we're calculating the ionisation energy. So before I start on question 2, feel free to click off the video and try it for yourself first. So the following diagram shows the first ionisation energies of some period 3 elements. For A, draw a cross on the diagram to show the first ionisation energy of aluminium. So if we have a look at magnesium and we have a look at its electron configuration, it'll be 1s2, 2s2, 2p6, 3s2. And then if we have a look at aluminium, we have all of that. So 2s2, 2p6, 3s2. But we have an extra electron, 3p1. And what we know is that 3p is of a higher energy level than 3s. And so this means that this electron that we're going to lose for the first ionisation energy is actually going to be easier to remove because it's in a higher energy level. And so the cross should be somewhere about here because it'll be much less than magnesium and it'll also be less than silicon because silicon has an extra proton. The atomic number has increased by 1, and so the ionisation energy of silicon to remove that 1 electron, it will be higher than for aluminium. And then for B, write an equation to show the process that occurs when the first ionisation energy of aluminium is measured. So again, the definition of first ionisation energy is the energy required to remove an electron from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. And so we have 1 mole of gaseous aluminium, and we're forming 1 mole of Al+ ions and an electron. And then for C, state which of the first, second, or third ionizations of aluminium would produce an ion with the electron configuration 1s2, 2s2, 2p6, 3s1. So aluminium we worked out was 1s2, 2s2, 2p6, 3s2, 3p1. And so now we just work out how many electrons we're removing to get to 3s1. So we're removing the 3p1, and then we're removing the 3s2, and then we get onto the 3s1. And so that means that we've lost 1 electron here and 1 electron here. And so we must have the second ionisation energy, because the first ionisation energy we would have lost the 3p1, and then the second ionisation energy we would have lost the second electron in the 3s, so this 3s2 electron. And so then that would leave us with the 3s1. And so the answer is second ionisation energy, or second ionisation. And then for D, explain why the value of the first ionisation energy of sulfur is less than the value of the first ionisation energy of phosphorus. So if we have a look at the electron configurations, we have sulfur is 1s2, 2s2, 2p6, 3s2, 3p4, and then we have phosphorus, which is 1s2, 2s2, 2p6, 3s2, 3s3. And so it's not really that obvious, 3p3, sorry. So it's really not that obvious why sulfur will have a smaller ionization energy than phosphorus, like we can see on the graph here. And if we draw out the energy levels, it actually becomes a bit clearer. So we have a box of 1s2, then 2s2, 2p6, 3s2, and I'll also draw out 3p6. So this is increase in energy. So these are all the energy levels. So if I fill out for phosphorus, so we've got 1s2 and 2s2 and then 2p6. And remember that they always fill out individually first, so that's 2p6. Then we have 3s2, and then we have 3p3. So phosphorus has this kind of electron configuration, but sulfur has an extra electron here. because it's 3p4. And so what that means is that this electron here, or one of the electrons from this suborbital, is much easier to remove. And that's because there's repulsion from the two electrons in the same suborbital. So we've got repulsion from the other electron. Compared to in phosphorus, when we just had three of them separately in their own suborbitals, then it's actually harder to lose one of those electrons compared to one of the ones in this suborbital box because of the repulsion between them. And so that's why the ionization energy of sulfur is smaller than that of phosphorus. And the last question says, identify the element in period 2 that has the highest first ionization energy and give its electron configuration. And so if we think about it, so we know this trend of period 3 elements, and we can just apply this for period 2 because the trends repeat every single period. And so because chlorine has the highest first ionization energy for period 3, that means that fluorine must have the highest ionization energy for group 2. Because in general, the ionization energy increases along a period because of the increasing nuclear charge. And so the outermost electron feels more attraction to the positive nucleus. And so it gets harder and harder to remove the outer electron when you go along the period. And so fluorine will have the highest ionization energy, the first ionization energy. And the electron configuration of fluorine is 1s2, 2s2, 2p5.